I'll just wait for 3 minutes. 9:30 is when we're supposed to begin, right?
That's correct. That's
yeah. I see there are quite a large number of people over here, about 130.
Right. So we've actually had over 450 registrations. So I guess there will be people joining along the way.
Amazing. The amazing thing about this COVID enforced remote everything, remote presences is that now we can actually hold these sessions and have people from all over the country, all over the world attend without having to move. And this has been particularly convenient. When I teach in CMU, sometimes, you just wake up with a cold, you have a flu, and you can barely drag yourself in front of the computer and teach. So then I just call up one of my friends and say, Berkeley, and say, Gerald, can you do a guest lecture for me? And it's 4 a.m. for the poor guy. And he says, sure. And he does it from 6 to 7:30. And this was just impossible in the past. And now we can do it. It's amazing.
Yes, so there are a lot of positives that have come of COVID too, right?
Yeah. I mean, in a normal world, this would have required me to travel to Delhi, which I wouldn't mind, honestly. But, the fact that I can do it without leaving my home is something.
I mean, we actually, had physical space restrictions in Subudh, right? We only could take 35 students at a time for our 6-month program. And the moment COVID hit, we doubled that to 70. And we doubled it, in fact, tripled it after that. And we have, more than 150 students that are actually doing the courses that we do now in Subudh. And we actually had students even from Nigeria that were actually
my, right? That is very impressive.
So it was really enjoyable, that whole exchange, an international exchange that was happening. We had students from New Zealand, Canada, Germany, and the US, along with this Nigerian student who joined all of the Indian cohort that we had. But anyway, it's time now, Bhiksha, so I shall pass over to you.
So my clock says 9:29. I'm assuming that there'll be a couple of people here.
Yes.
Who want to come in at exactly 9:30. So I'll just wait a few seconds.
Sure. So my father worked for the Indian Railways, and things were always running a little late there. I was trying to bring some German influence in here, and we're going to try and keep it at the time.
That's okay. So it's 9:30. Good morning, everyone, and thank you for listening to me. So before I begin, I want to tell you that although this is a master class on deep learning, my keynote is not going to say anything about deep learning. This is, you're going to be hammered with several days of deep learning. I thought I might do something different. I will actually talk about very high levels of what is AI, what is machine learning. I will not throw any equations at you. In fact, everything over here is something that should be child's play for you. So you're probably listening to old stuff. It's probably a redundant lecture. I hope it is. And that's often the best thing I can say when I'm doing a keynote. So let me begin by introducing myself. I'm Bhiksha Raj. That's what I look like when in person. And I'm a professor in Carnegie Mellon University's Language Technologies Institute, which is in the School of Computer Science. I have affiliate positions in the machine learning department, music technologies, and electrical and computer engineering. My areas of research include speech and audio processing primarily, which is what I worked on for a long time, and machine learning. But for the past several years, actually a decade now, so it's been a long time, I've been working on privacy and security and deep learning as well. And we have some very nice papers on the topic. If you're doing any work on any kind of verification using deep learning models, you're probably using something that we did in my group. So this is my campus, Carnegie Mellon. It's a small campus. It's taken obviously from a very nice angle, which makes it look very beautiful and green. When you actually go there, it doesn't look quite as nice, but still, this is the picture we like to show, taken from a drone, of course. And somewhere here, where is my office? I don't think, yeah, my office is somewhere out there. Anyway, so this is a This is supposed to be an interactive lecture, at least in part. So I'll ask you questions and I'll pause and wait for answers. Not too many, one or two or three, just to keep you engaged. And had this been an in-person lecture, then I could have actually poked fingers at you and invoked individuals. But now I'm hoping that you will actually respond and that I don't find myself in the embarrassing situation where I ask a question and nobody responds. So let's begin. Everything that you've learned, that you've been hearing in recent times about AI sounds very science fictional. So what exactly is this AI? Here are all the various bits of jargon that you might have heard. Artificial intelligence or machine intelligence, machine learning, deep learning. What are these things and how do they relate to one another? So we're going to spend a bunch of this lecture just trying to get a very high level, children's level understanding of the various jargon and how they relate to one another. So here's how artificial intelligence is defined by Oxford Dictionary. It says AI is the theory and development of computer systems able to perform tasks that normally require human intelligence, such as visual perception, speech recognition, decision making, and translation between languages. That's from the dictionary. In layman's terms, an artificially intelligent system is a computer system that exhibits behavior that, if performed by a human, would be considered intelligent. But what is machine learning? Machine learning is different from artificial intelligence. Machine learning systems are computer systems that learn from experience. In the case of computers, experience equates to data. So when you compare the two, AI corresponds to systems that behave intelligently. Machine learning corresponds to systems that learn to behave. So what is the difference? Again, if you have any questions at any point, folks, please feel free to interrupt. I'm always happy to take questions, okay? So to understand the difference between AI and ML, let's start off by building a game. I want to build a computer chess game that beats world champions. Now, those of you who are aware of the history, the first computer chess game that actually beat a grandmaster was built back in the late 1980s, 1989 or thereabouts, as a PhD thesis in Carnegie Mellon University. It actually beat a grandmaster, and then this was called Deep Thought. So then the person who built it went to IBM and took the ideas with him, of course. So in IBM, they built Deep Blue. This was in 1997. And Deep Blue played Garry Kasparov. He was the world champion at the time, and it beat Garry Kasparov. In fact, it was a bit of a controversy because in the first game, Kasparov beat the game because the game made a mistake. And then they updated the algorithms between the first and the second game, and thereafter, no human champion has ever beaten the best computer game. But Kasparov wasn't too happy about losing the subsequent games, and he claimed that they purposely let him beat the first game just to soften him up psychologically. Anyway, stories apart, if you have a computer chess game that beats people, a computer chess game in general, is this artificial intelligence? How many of you think it's artificial intelligence? Just give me a yeah or nay. Raise your hands, sir. Right, you have a hands raised. Raise hands on. I like to count these things. Right? So, there are 140 people here. I hope to see at least 50 hands raised, or if it's a yes question. Quite a few. All right. So I think we have enough. Now, so how do I build such a game, right? Let me go ahead and build such a game. Lower your hands, please, because I'll keep asking you. One simple way to do this, I can just make a list of game rules. making a list of game rules, queen goes up diagonally, the knight jumps up two positions in one direction and one position in the other. These are just rules, but a game that plays randomly by these rules is not intelligent. It's not going to win anything, right? So what makes this game intelligent? We need a way to select the right move at any time. And so we can do something like this. We can handcraft a table of rules for the best moves. So you can put in a whole bunch. If the rook can take the bishop and the bishop is unprotected, take the bishop with the rook. So this is a whole bunch of rules which give you some set of best principles. And if you have a collection of such rules, you can actually build a game that will a computer game that will beat humans. It will beat several of them. And in fact, this might even beat many of you. This is intelligent. This is AI. But this AI will not beat a champion. Why? Because while it's technically feasible to write down all the rules required to win a game, the number of rules required to make a winning game is exponentially large. The number of game states in chess is about 10 raised to 120. And so you will need at least 10 raised to 120 rules to know what is the best move to make from any position. We are not going to sit down and tabulate all of those rules. Mind you, if you did, you would have a chess game that would beat humans, every single human. But the point here is that you cannot actually tabulate those rules. But even if you halfway tabulate those rules, it's still going to be an intelligent game. It's going to be AI. And in fact, this is what early chess games did. If you went back 25 or 30 years and you played computer chess, those things typically had bunches of rules that they played by. Let's try to improve on this. How would we do it? We are going to do by learning from experience. So you learn by playing or by observing. And so you observe what positions are typically winning, what positions are typically losing, and from that you learn to play the game. So let's formulate this. Again, we're speaking of computers, right? So let's formulate this. Let me start off by drawing a diagram. So in this diagram, every circle is a game state. A game state is a board position. And like I said, there are 10 raised to 120 of such board positions. I'm obviously not showing all of them. And not every game position can lead to every game position. So those arrows show, for instance, that if you're in this game position in the middle, can you folks see my mouse?
Yes, we can.
Yes, sir.
So if you're in this position or in the game, these may be the only board positions that you can go to. So these arrows show you potential moves that you can make. I won't actually show the arrows because there are going to be too many of them, but you get the idea, right? So each state can move into one of n surrounding states depending on the opponent's moves. Now, in the beginning, you have...
Ayush, you need to mute.
Okay. So in the beginning, you have all of these states, and you don't know which are the good ones and which are not all, and which are the bad ones. In the beginning, you're starting off with a completely agnostic view of the world. Then you begin playing. You play a very large number of games. So let's say you play your first game, you drag your poor brother or sister down, and you begin playing with this person. And the first game you play, you lose. So then based on the fact that you lost, you're going to surmise that all the game states that you moved into led you to losing. And so you'll go and say, put a little bit of red color in every one of the game states that you visited when you lost the game. Except that you're not going to, so I'm missing some slides, some pictures, except that you're not going to give the same amount of red to every one of these positions. So let's say you had the sequence of moves and you ended up losing. then you can be fairly certain that the game position that you were in, very close to the loss, definitely led to the loss. As you go back in time, you're less and less certain that they actually contributed to the loss. So as you go back, the amount of red that you're going to put in the circle is going to fade. So that you'd make this, you put a lot of red out here, a little less here, a little less here, a little less here. But anyway, the point is you're going to color all the moves that you made and say these were bad moves. Then you play another game. You lose the next game. You add more colors. You go back and recolor all the game states that you visited when you played that game. I mean, you add colors. And some of these states might have been visited even during the first time you played. And you add red to a little bit of all of the game states that you visited when you played this losing game. And then you play another game, and this time you win. So now these are the game states that you visited during this game. You're going to imagine these were good game states. So you will add a little bit of green to these things. And again, as you go back from the winning position backwards in time, the amount of green that you're going to add is going to fade. But still, think of it as adding a little bit of green color to each of the game states that you visited when you played. So you continue playing this game, continue doing this, playing lots and lots of games, and each time you win or lose a game, depending on whether you lost or whether you won, you're going to add a little bit of either red or green to all the board positions that you visited when you were playing. And the problem with the strategy is that if all you did was play one game every femtosecond, from the day you were born till the day you died, the number of game states that you're going to visit is going to be essentially a zero fraction of the total number of possible game states. So that's not enough. You can also learn from your opponent's moves. When you won a game, your opponent lost. When you lost a game, your opponent won. So you can also say, if you won the game, you can say that all of the game states that I visited deserve a little bit of green. All of the game states that my opponent visited deserve a little bit of red. And so now you can double the amount of experience that you've got. You can watch other people play. And from their games, again, you can begin coloring the game states. You can go and read up books. You can dig up volumes of literature on chess and pull up all the examples of all the games people ever played and color the game states they visited as well. All of this is going to still not fill up too many states. So to really speed up matters, you can begin playing with yourself. Just play both sides of the board. And if you're a computer, you can play against yourself, and the games can be terribly fast. So you can play hundreds, thousands, or millions of games in a day. And as you keep visiting the states, you keep coloring them. Eventually, you're going to get lots and lots of board positions with different shades of green or red or various shades of yellow. Game states that always led to a loss are going to be mostly red. Game states that always led to a win are going to be mostly green. Game states where you sometimes were lost, where the future sometimes led to a loss and sometimes to a win, are going to collect both red and green dots. They're going to be somewhere on the continuum between green and red. There could be yellow, orange, whatever. But the color that you've got, yeah.
Sir, I have a question. Like sometimes the grandmaster or the champions have 2400 elo around that, right? And a computer has the option to either play 2400 or 2000 or 1600 elo. So basically, computer knows how to play best chess, but he chose not to. Like I've seen a game with computer versus Vishwanath Anand. And the bot he was playing against was Vishwanath Anand only, because that match was drawn. So computer knows how Vishwanath Anand plays.
So again, the point here we are trying to make is not about a specific player. So think about this. And again, this is a very high level idea that I'm giving. I could get into a lot more detail on the actual how you would learn to play a chess game. But from the perspective of a chess game, think about this. Suppose you win. You make a move, you checkmate your opponent. Then the board position that you found yourself in is a winning position. It doesn't matter who was playing, it's a winning position, correct? So that's got to have maybe a goodness score of 1. My color here represents a goodness score. Suppose you lost, then the last position you were in almost, well, definitely led you to lose. So that has a score of -1. Then as you track your way backwards, you can assign these scores to every single state. Now, there's a lot of mathematical theory and there's much that's unknown about chess, but the general assumption is that they're either white or black must definitely have a strategy to win. The general assumption also is that regardless of every position of the game position, every position in the optimal condition, if everyone plays really smartly, is either definitely going to lead to a loss or definitely going to lead to a win. So in theory, going by that theory, every dot over here is going to be either bright red or bright green, because there is a strategy that will lead to win or lead to a loss, or lead to a loss, or the best strategy might lead is either definitely going to lead to a win or to a loss. Except that we don't know it, right? Because it's impossible for us to explore the whole thing. This doesn't matter. It doesn't matter who is playing. The real difference between the various experts is on how well they've figured out how closely they've come to the optimal strategy from any given board position. That's about it. So, but there is in the absolute sense, there's an absolute goodness score for every board position, which tells you if you play properly, how likely it is that you're going to win when you're in that board position. That's about it. So that's all we're trying to determine. Did that answer your question?
Yes, sir.
Yeah, right. So when you play better players, they are employing better strategies. So the kind of game positions that you're going to are going to be maybe more definitively winning or more definitively losing, because these players are good. But at the high conceptual level, that's not really an issue. So at the end of it all, you're still going to have visited only a very small number of game positions. So you're going to have a great many blank positions that were never visited in all of our practice games. In fact, the vast majority of the positions are going to be unvisited, all of these black squares. So what we can do is we can learn a function from the colored states to the goodness value that you associate with those states, and use that function to color all the blank states. And now that you have colored all of the states, during the game, let's say you find yourself in some position in the game, in the board, say the black one, that's your current position. Your question at each stage in the game is, where do I move? And you can do a couple of different things. You have to move to one of the adjacent states. You can either move to the greenest state, which gives you the highest assurance of victory, or alternately, you can play defensively and say, I'm going to move to a state which gives my opponent the least chance to win. So remember, when you play a move, you're going to move into some state, and then the opponent is going to play from there. And the opponent may move the board into a red state, which is a losing position for you. So you want to identify a move such that the opponent's best path leads to the least red state. You give your opponent the least chance to win. This is basically how the automated games are usually played. But anyway, so at a high algorithmic level, at a high conceptual level, this is how you would build the chess game. And in fact, you could literally just code this in. So what did we just do? We learned from experience. We modeled the problem. Here, we modeled it as a graph. We observed data. either from our own games or from others' games. We had a model, so we learned the parameters of the model, which is the function from the position to the value. And we used the model to make predictions. In this case, we predicted the scores for all the blank positions, which we can use to make the most useful move. And we used several concepts. So what we sort of learned how to perform, or when I say we, the system, learned how to act intelligently from experience. So machine learning was used to learn how to perform an artificial intelligence task. And in the process, several concepts were invoked: graph theory, probability, algorithms, whatever, right? So at a high level, there is a distinction between AI and machine learning. AI is the actual task itself. Our AI is the system that played a game in an intelligent manner. There are many ways of making it do that. Learning from experience to act intelligently was machine learning. And machine learning is what we use because of our natural inability to simply elucidate every possible scenario in the game that you could just hard code into your artificial intelligence system. So this is at a high level, right? Now let's go back and figure out what is this business of intelligence and artificial intelligence. I'm going to try to equate. Now, intelligence is something that's uniquely human. When we think of intelligence, we know, yeah. Is there a question?
I'm sorry to interrupt. Yes. Sir, I wanted to ask, in the chess game, how is the machine intelligent? We are just feeding the machine the examples of how we played and the large number of...
So literally, right? How did we define intelligence?
No, what I'm trying to say is that it will be biased from the start towards winning.
That's what it's supposed to be doing, right?
Then it's not thinking like human. For example, I am playing and I'm the opponent, and the machine is biased towards winning, going through the same path as it's defined, that these spots are where you will win. But as a human, I can think of how I can defeat, but the machine cannot, because he's literally following the path.
The machine is thinking of how to defeat you, right? So stop thinking about what's inside the machine. Put a box on the machine, okay? And let's say you don't know what's inside the box, whether it's a human or a machine. Then if that entity inside the box played that game, would you think that entity was intelligent?
Okay.
Right?
Yeah.
And then you take away the box. If there's a human, it's a naturally intelligent entity. If it's a computer, it's an artificially intelligent entity. That's it.
Okay, sir. Got it.
Right?
Thank you.
So that literally is the definition of the whole thing.
Hello?
Right? Yeah.
Hello, sir. If there is a competition between two AI, then who will win?
The AI that does a better job of learning will win. The AI that has more compute power will win.
There was a match between the two AI, and almost every case is white won.
So if that is the case, there's a lot of mathematical theory that says that white will always win. I mean, it's still hypotheses because we haven't actually proved it for chess. There are other games where you can prove that one or the other player will always win. But I don't believe we have anything of that kind for either Go or chess or some of these other games. And it's very likely that white will always win. And that's basically what we saw, that the AI has figured out something pretty close to the optimal strategy, which means that even if the opponent plays the optimal strategy, the white is always going to win. Now, we don't know. That might just be the case, right?
Because in chess, always black has to counter attack. Like if the guy is playing King's Gambit, he has to play counter King's Gambit.
So that's, again, this is a hypothesis or a speculation, right? You don't know that making the first move puts you at a disadvantage. We don't know this.
Okay.
Right. So unless it's mathematically proven, you can't make the claim.
Then, sir, AI will gain more experience with playing with another AI.
AI, so actually, let me complete the talk, right? Let me get to at least my halfway point where we might just stop, and we'll come back to that question, okay?
Okay.
But let me ask you another question. Are these two guys the same people? I'm going to equate artificial and natural intelligence, you with a computer. Are these two guys the same people? Raise your hands if you think it is. They are. How many of you think these two are the same people? Okay, most of you think they are the same people. You're right, okay? What about these two guys? Are they the same people? Everybody agrees that they are not, right? What about these two guys? Are they the same people? And I believe the answer is no. One of them is James Franco and the other is a lookalike. So I can't vouch for it, but I believe the answer is no. Okay. What about these two guys? Are they the same people? Again, John Travolta, right? Both of them. So you can make out from the dimple and the chin. So here is the question. I mean, you were right on at least three or four of the queries. And you're intelligent, right? How did you do it? How did you actually do this? Can someone tell me how did you decide that these two people were not the same? Anyone? Matching features. So you're going to say the chin is in trying to match details. If I ask you to actually enumerate it, you're going to find yourself somewhat challenged, right? Because when you thought about it, when I gave you the picture, you didn't say one chin is more pointy than the other. One nose is slightly different. That one forehead is slightly different. It just happened. As Mukul points out, it just happened immediately. Now, and yet when I ask you, you begin making rules. So how can you make a computer do it? Point is, you cannot just make a table of rules because the rules you gave me came post facto and your answer was instantaneous. So what are these rules if I want to make a table of rules? If I want to make an artificially intelligent system which does the same thing, what rules do I use? What features do I use in these rules? Now, if I asked you about what rules you used, you can probably give me some rules. You can say, if I go back to this guy, if I forced you to give me answers, you're going to say the chin is different, the ears are different, the forehead is slightly different, the cheek is different, the eyebrows are different. You're going to give me all of these rules. But then how did you actually learn all these rules? How did you actually learn all these rules in your own real life? So here's what happened. You learn these rules from experience, by observing. You had an uncountable number of facial images. All your life, you've been observing the world. And you encountered innumerable examples of facial images that are from the same person, and an even larger number of examples of facial images that are not from the same person. And from this vast exposure to incredibly large amounts of data, you have sort of internalized some way of figuring out which ones are, when two images represent the same person and when they do not. And in fact, you're even able to do it when there's considerable variation. For example, if you saw this top right corner, you'll be able to tell me that both of them are Tom Cruise, even though those two pictures are taken 20 years apart, and he actually looks very different, right? But you can't really enumerate the rules. Again, like if somebody says divide the thing into parts and check, if I begin looking at dividing it into parts and check, the two pictures to the over here of Tom Cruise are going to look very different, but you didn't do it. You just got it right. You can't really enumerate the rules because the rules are abstract. So here is the human method for learning. You have large numbers of examples of positive and negative matches. Based on these, you compose some abstract, indescribable model in your head. And then when you get a new pair of faces, you're using this abstract, indescribable model to decide whether they are the same person or not. So we learn to recognize faces from seeing many examples. And then we use what we learn to recognize people afresh. So the learning process is what's in the gray box. The outcome is this abstract, indescribable model in your head. That's what is finally used when you actually process new faces. So why did you actually have to go through this? What was it about the learning process that you went through in life that made you learn this abstract model that let you recognize faces? That's evolutionary, right? So way back when we were all in caves, these are the kinds of things that happened. You mistook an enemy for a friend, you ended up prone. And if you mistook a friend for an enemy, you displeased the guy, you ended up in the same situation. So you had this evolutionary impetus to learn. If you made a mistake, that could often mean a quick and grisly end to you. And the people who actually survived are the ones who didn't make those mistakes. So there was a cost associated with making a match when you shouldn't, or not making a match when you should. There was a cost. Suppose you want to build a computer equivalent of yourself. The process is the same. You want to learn a model from observing loads of examples, lots of positive and negative matches. You want to put them through your model. You get an abstract, indescribable model. And then that's in the learning phase. Then during the operational phase, you put in new sets of pictures. It goes through the model. Out comes a match or no match answer. So you use this model that you've learned to operate on new data. So to do this, here are the things we need. We need the examples, of course. We need training data. Things that are instances of positives, instances of negatives, so that we can learn from them. We need a computational model for representing what we learn. So your computer is a mathematical object. It's an algorithmic object. It needs structures. So this structure is your computational model. You need some kind of a data structure, and the appropriateness of the structure will limit how effective your model is. Then finally, you need you need a criterion to know how well the system performs. In other words, you need a cost of failure. If this cost of failure is improperly defined, then again, you're not going to learn very well. You need a learning algorithm to learn the parameters of the model. The computational model is this box, which can be shaped. You learn your criterion to shape it, but then you have an algorithm that shapes your model according to the criterion. So you need a learning algorithm to learn the parameters of the model. And then finally, you need a mechanism to use the model once learned. This is what we call inference. All of these are implicitly part of the process, the computer process, the computer method of machine learning, of learning from experience. And one of the biggest challenges here, the rest of these can be mathematicalized reasonably well. The biggest challenge is this criterion to know the cost of failure. To know the criterion to know how well you're doing. And the issue is, once the whole system is learned, that system is going to operate by the criterion. But if in the case of a computer, how the system actually operates may be something that's opaque to a human. It may not make any sense to a human being. So going back, I'm going to keep looping back to this question. What is machine learning? It's the science of learning to perform intelligent tasks from data. By intelligent, I mean really smart. Now, the traditional anthropomorphic definition is this action would be called intelligent if a human did it. So is recognizing faces intelligent, or being unable to recognize them really dumb, right? If the answer is yes, and if a computer can do this, then you're going to assign the same terminology that you applied to the human to the computer. So AI, artificial intelligence, refers to systems that can perform intelligent tasks. Machine learning refers to systems that learn to perform from experience, like the chess game or like the face detector. So it's learning to perform intelligent tasks by observing data. Machine learning produces AI, but not all AI requires machine learning. So to drive the point home, how many of you read Roald Dahl? I'm sure all of you have read some story or other of Roald Dahl's. I'd like to see some hands raised. Charlie and the Chocolate Factory, James and the Giant Peach, Matilda. There must be thousands of you who have read, or hundreds who have read Roald Dahl stories. And okay, and how many of you have read this story, The Great Automatic Grammatizator? Has anyone read this one? Anyone at all? No? Okay. So it's a very beautiful story. Roald Dahl didn't write just children's stories. He wrote a lot of stories for adults. And so this one, The Great Automatic Grammatizator, is a story about a machine that a mechanically minded man builds. He reasons that the rules of grammar are fixed by certain almost mathematical principles. By exploiting this idea, he's able to create a mammoth machine that can write a prize-winning novel in roughly 15 minutes. He composes and constructs the entire machine. Then you type in the general theme. You type in all the desiderata that you want from the story. Punch them in. Hit a lever, and it prints out a book. And these books begin winning Pulitzer Prizes. And pretty soon the machine puts all authors and poets out of business. That's the story. According to the definition we just saw, would this be AI? Yes or no? Is this AI? Raise your hands if you think this is AI. Quite a lot of you think it's AI, right? Just 9? I'm sure more than 9 of you think it's AI. So, okay. Some of you thought it's ML. What do you mean by it's ML? What was the distinction? So we just stated that machine learning creates AI, correct? So machine learning is a process of generating AI. But this is definitely, so it's doing something very intelligent. It's writing a novel. Isn't that intelligent? It is, isn't it? So this is definitely AI. But let's go back to the question about ML. Is this machine learning? How many of you think this is machine learning? Raise your hands. The answer is no, right? This is not learning from experience. Somebody fed in a bunch of rules and it learned, and based on this bunch of rules, you give it an input, it produces an output. There is no further adaptation going on to interaction with the world. But now suppose this machine's books go to the bookstore and the machine's rules, machine adjusts its own rules based on whether the books sell or not. would that be machine learning? Right. The machine has learned from experience, right? So the machine has learned, it was always AI, but only when it learns from experience is it machine learning. That is the distinction. AI is just any system that if you covered it with a box, you're likely to confuse it for an intelligent entity, and there is maybe a human being. But if you pull off the box, you see it's a box. It's a machine. Machine learning is when it learns from its experience. So now here is the problem with learning from experience. Now this is fun. I'm going to show you a problem. I want answers. Here is a short series of numbers. I want to see answers in the chat box. Can you guess the next number in the series? Anyone? Can anybody guess the next number in the series? 8, 7. 7 is already there. 8. Any others? Okay, so wait. You think it's 8? Okay, clear your answers. I'm going to show you the next one. Now, can you guess the next number in the series? Ten, 11, 11, 11. Okay. Right, now can you guess the next number in the series? 12, 13, 12, 13, 11, 13, 12. Okay, now can you get the next number in the series? Four, 13. I'll wait for 3 or 4 more answers before I reveal the answer. 12,500. 500. I like this. Yeah. I'm not sure where 500 came from, but yeah, 500 is actually a good answer here in this case. But this is the sequence of non-negative numbers which don't have the letter T in them. And I'm going to take a bet that none of you thought of this answer. And the reason you didn't think of this answer is that you got fooled by the numbers. You need to know what kind of model to consider. When you just see the data, there are any number of models that can fit. And each of you fit a different kind of model in your own head. Every one of you is wrong. So the issue is, if you get the model wrong, you're not going to get the answer, right? The problem with learning from experience is the problem of modeling. And you're modeling, and just looking at the data does not tell you, does not even get lent to a hypothesis very frequently of what is a good model. And secondly, maybe one of you have guessed this model, but you cannot really be sure of it until I show you a lot more data to validate it. So you need sufficient data to validate the model, and the amount of data that you see required may be very, very large. But the point here is the model in your mind, the obvious looking model, may be very far from the ground truth, and that's going to make all the difference. Now, here's another question. How many of you think these two are the same guy? Raise your hands if you think these two are the same guy. Yes? Nope, not same. Yes. Yes. 80. Observe something very interesting. Suddenly, the sheer certainty that we had the first time around has disappeared, right? How about these two? Are these two the same guy? No. Okay, it turns out the answer is yes. What about these two? In this case, you're going to say no, simply because you just saw the same picture a few seconds ago, right? But the point is, you got it wrong here. Everybody was confused here. And here, you were using prior cues. But what happened over here? The model ended up being specialized to the task. In your case, what was the model that your brain ended up being specialized to? Can anybody tell me? Because the pictures are inverted, right? It wasn't even faces that you have learned to recognize. You have learned to recognize faces that are upright. If I take the same image and I flip it upside down, your ability to recognize faces. Was there a comment? So your ability to recognize faces just vanishes. There's a lot of research over here which shows that when people are shown upright faces, they're extraordinarily good at recognizing and matching faces because we have a very specialized face detector built into our brains. It's needed because it was needed for survival. But then you show them the same pictures upside down, and their ability to recognize and match faces becomes approximately the same as their ability to match pictures of trees. No different. Because once you turn the face upside down, it becomes an object like every other. So the model, in your case, was specialized to recognizing upright faces. This is exactly what will happen to the computer as well. The model ends up being specialized to the task. And so these are all the risks of learning from experience. So anyway, just sort of moving on, what can AI do? AI can do a whole lot of things these days. It can do, it's used to play games, to drive cars, to predict the stock market, medical diagnoses. Those of you who saw the IBM system winning Jeopardy, there was almost no machine learning in it. But it was pure AI. And you actually find AI systems that perform astrology. Obviously, there's no such thing as learning from experience in astrology. It's purely rule-based. And whether it's intelligent is something that's questionable, considering what astrology is like. But yes, you can find an AI system for astrology. What can machine learning do? It can learn to do all of these. And machine learning can learn to do these things better than a human being. And it can often do things that a human cannot do. Now, folks, just give me a couple of seconds. I'll be right back. Just give me a couple of seconds. Sorry about that. This is another of those things that happens with Zoom, right? So anyway, yeah.
Sir, can you explain the idea behind like telling your future with AI?
How does your astrologer do it? He has a whole bunch of rules. He can code it in, right?
Yeah, okay, sir.
Yes, sir.
That's it. You cannot learn to do it because clearly what your astrologer does is also fairly random. So you can have an AI system in that I can put a box on the system. I can put a box on your favorite, which would be the same. But here's an example where machine learning is simply going to fail, right?
Yeah, okay.
So that's why I put it there as an example of an AI that's not machine learnable. Now, but again, people believe in astrology, so that's why it's AI. It's if we are playing with a bot, if we keep the steps twice, will it find what? The question is incomplete. Okay.
Hello, sir. Am I audible?
Okay, I don't know the question, so let me continue. Right. So
Hello.
yeah.
Sir, actually, I want to say that like we are if you're playing with a bot, sir, with a live bot, with not a computer system. If we unfortunately keep it steps twice, like if we keep, for example, if we move an elephant and another thing, will the opponent will find our step?
I'm not sure I understand your question, but a bot is a computer system.
So like I'm saying that like if you're playing with a robot, for example, the rule is that each person to move a single step, right? Initially we do a step, then the robot, then robot. If we make two steps, which the robot does not recognize while playing.
Yeah, so that's again part of, that's an interesting question, right? I haven't actually thought about it, but presumably if you make two steps, if the outcome is the same as if you could have achieved in a single step what you did in two, there's no, as far as the outcome is concerned, there's no distinction between the two. And if the outcome cannot be achieved in a single step, then obviously this is something that is discernible, that can be found, right? Now, any rules about these, any kind of, again, you're speaking of, this is hearkening back to essentially having the right model and the wrong model. And that's a very good question. If you want the robot to be able to discover all of those, then this has to be part of your model or your model is going to fail.
Okay, sir.
So anyway, these are all the things the machine learning system can do. They can play games, they can drive cars, they can perform medical diagnoses, predict the stock market, answer questions, and maybe even tell your future, and often do these things better than a human, and often do these things that a human cannot do. Why do you think that would be the case? Anyone?
Due to its computational powers and storage capabilities?
Not getting tired, human bandwidth, complexity, all of these are, exactly the reason. But there's more. The biggest thing is replicability and repeatability. If you give a computer the exact same input twice, it is going to give you the same answer twice. In other words, a computer diagnostic system is going to be much more consistent than your human doctor. And that's often something that's very important in systems such as these. So it doesn't get fatigued, and it's going to stay consistent. This is huge. So it's meta-human in its ability. Secondly, the number of games, think of chess, the number of games you can read about and you can play and you can watch in your lifetime is minuscule compared to what a computer can do. So they are just way better at storing and retrieving vast amounts of data. And when it comes to raw computation, they can compute orders of magnitude faster than you. And their model space, counter to anything that you might believe, the space of models that a computer can consider and evaluate is much larger than what we can, because we are conditioned by evolution to thinking in some very constrained ways. And so, in fact, computers can even learn from vast amounts of data and summarize them for human consumption. So a machine learning system that learns to do what a human can do, but from data, if constructed well, can surpass the teacher trivially, which is why no human is ever going to dream of beating a computer chess game again, or a computer Go game again, or a computer backgammon game again. They're just going to beat you every single time. A computer self-driving car will actually drive better than a human. Whether we are, we are acceptable, we are willing to accept the kinds of mistakes it makes is a completely different problem. But the fact remains that it's going to be just better than what we do. So, and of course, there have been any number of machine learning successes: Google, Facebook, Walmart, working for tasks it performs: information retrieval, question answering, image recognition, speech rec, personalization, recommendation, pathfinding, self-driving cars, medical diagnostics, weather prediction, predicting hospital readmissions. All of these use machine learned artificial intelligence. And I think it's quite unquestionable that they do these things way better than a bank of human beings can. Before automated search came in, Yahoo used to have people trying to respond to questions. And you know how badly it worked, right? I don't think you can get, if you put all the people on the planet at work trying to respond to the kinds of questions Google gets, together they're not going to match Google servers. So these are just machine learned systems, AI systems that have, observe that I'm saying machine learned AI systems. This is AI that has used ML as part of its construction. They are just better than humans. And they can do all kinds of things like assigning categorical values. You know, is this a pot or a potato? Soft classification. I'm 50% sure it's a potato. Estimating numeric values. Look at the footprints and say this person is 183 centimeters tall. Prediction. The Dow index is going to be 20,000 tomorrow. Or which can be numeric, or it can be categorical. The Dow is going up, or the next best move to make is queen to J3. All of these things that the machine learning system can do from learning from data, right? So I've sort of, there's not a lot of continuity in what I've been, on the slides I've been putting together. And I had a natural stop at this point. So although maybe this wasn't particularly enlightening, I have the option of stopping here or boring you for the next half hour. I'll roll that choice to you.
Please go ahead, Viksha. But one question before you go ahead. You talked about how humans also require large volumes of images to, pairs of images to discriminate between them. But cognitive scientists would argue that that's not the case, right? One of the big differences between deep learning and human intelligence, they say, is the fact that we can actually learn very quickly with a very small number of images and abstract away.
So it's not really, the debate is in a slightly different direction. The debate is about, what are the kind of biases built into the model that we have in our head?
Right.
And that is answered better by this one, right? So we have fine-tuned, our evolution has fine-tuned our brains to pick up cues in a specific way. And we've built our models to be very specific to perform the kinds of tasks which are really very important for survival. If you really want to compare humans to machines, I think the place to look at is unnatural tasks, things that are not naturally part of our experience. And if you compare a machine to a human, you're going to find the machine beats the human every single time. It's just that we have managed to evolve these beautiful biases into the composition of our brains, which makes us much better at learning than machines in certain tasks. But then you go outside, go to a completely novel task, which is outside the domain of human experience, I think we're going to find ourselves in a pretty bad position. So anyway, now going back, I still haven't mentioned deep learning, right? So I'm going to take a look at classical AI, classical ML, and a natural progression of thought in some sense. Classically, when people first built artificial intelligence systems, they sort of tabulated or graphed knowledge, rules, and instructions. They basically would feed in lots of information, they'd feed in rules, they'd feed in relationships. Then you need some way of representing these. These can be tables, lists, graphs, and try to, given a novel situation, they would try to come up with answers. The system would try to come up with answers using rules for how these answers must be derived based on other rules and knowledge that have been fed into the system. And the problem was these things didn't work because it's impossible for us to feed in all the kinds of knowledge and information that is actually needed. So Marvin Minsky had this very nice project about 25 years ago where Pushpinder Singh, it was being done, it was the PhD student working on it was Push Singh. So he had people feed in nuggets of knowledge. And the idea that he had was people could just go to their website and feed in a fact, just type it in English. And their idea was that if you collected a sufficiently large number of them, millions, billions, trillions, they could have an AI system that would sort of sift through these and learn to be intelligent. So a couple of bad things happened. One, of course, was there were two different people working on the essentially the same project from two different places. And unfortunately, both of them committed suicide. So that was a bad thing. But more generally, the idea died a natural death. Because it turns out that when you begin tabulating things, look at what was happening. You were asking people to feed in snippets of information. And the idea was these snippets of information could somehow be abstracted into knowledge. So you were left with the problem of abstraction. And if you ask for explicit rules and bits of knowledge, it's really impossible to get them all. And that's where classical ML came in. Classical ML, classical AI was built on using knowledge and rules and instructions to make its deductions. Classically, machine learning rule systems were built as an aid to classical AI. We realized that you cannot really feed in all that knowledge. You cannot really feed in all those rules. So why don't we build algorithms that will automatically extract these rules from analyzing lots and lots of data? And if you have enough data, then you're going to have, and if you have the right formalism for extracting these rules, you're going to learn a lot. So here's a quick kind of walkthrough of the process of classical machine learning. Two common approaches that you guys are probably familiar with. I'm going to use a toy example. The 10,000-year drought. It's the year 13,000 AD, and the Earth has been going through a 10,000-year drought, thanks to climate change. They're even burning up the Amazon. So we need water. So the solution must be found urgently, or poor Californians are going to have to surf on hard sand because there is no water left on Earth. And so you and a friend, you're employed by the agencies of the time to hop onto a spacecraft, travel for 1,000 years in a sleep pod, and finally arrive at a habitable planet out in the Pleiades cluster. Your task is to find water and report back to Earth. So the way the crew has been set up, it's you and your friend. You're a pessimist. Your friend is an optimist. So you being the eternal pessimist, you say there's no hope. It never rains on GRX CY 2031. Your colleague is an incorrigible optimist. Oh, the planet is full of water. We're going to send it back to Earth. Earth is saved. So let's say you arrive on a day when everything is orange. There's a thick, smelly fog, and it's raining. So you start off from this belief system. You're going to update your beliefs. Instead of saying it never rains, you say, okay, I did find there, end up there on a day on which it was raining. But because you're the pessimist, you're going to say it only rains under the very specific condition that I saw. It only rains on GRX CY 2031 on orange, smelly, foggy days. Your friend, he's an optimist. See, I told you it always rains on the planet. So, he's happy, right? You circle the planet a few more days, you land on it. It's still orange and foggy, but there's no bad smell. The first time around you went there, it was orange, it was foggy, it was stinky, and it was raining. Now it's orange, it's foggy, there's no stink, and it's still raining. So you update your beliefs for your report again. So you have to update yourself.
Hello.
Obviously. Right.
Sorry for the interruption. I guess somebody's unmuted there.
Yes. Okay. So the thing that you're going to have to knock off from your hypothesis.
Hello.
Can everyone just mute other than Bhiksha, please? Please
mute your microphones, guys. Yeah. Okay. So you're going to have to knock off smelly from your hypothesis and say you're still a pessimist. So you're going to come to the most specific condition. It only rains on orange, foggy days. And your friends, see, we've been there twice. It rained on both occasions. It always rains on the planet. But then you visit a third time. And this is a beautiful, bright, clear day, but it's smelly and it isn't raining, right? So now you're going to say, aha, I told you it only rains on orange foggy days. You are not going to update your hypothesis. You are the eternal pessimist. But your friend, he's going to have to lose a little bit of his optimism. He says, okay, here are the conditions under which it rains. It rains if it's foggy, or if it rains if it's orange. He has to accept the broadest possible set of conditions under which it rains. So for him, an or makes more sense than an and. For you, an and makes more sense than an or. And so you begin revisiting the planet again and again, and you fill in your hypotheses. You said it's rains when it's orange, smelly, and foggy. Your friend said it's always raining after the first trip. After the second trip, it wasn't smelly, so you sort of fine-tuned yourself. It only rains when it's orange and foggy. And your friend says it's always raining. And then you visit a third time, and it's still, it's clear. It's smelly, but there's no fog. It hasn't rained. You don't need to update your hypothesis. Your friend does. He says it rains when it's orange, or it rains when it's foggy, right? You make more visits and more observations. And then finally you arrive on a day on which it is orange, but there's no fog and there's no rain. So would you be changing your opinion? Anyone? Based on this, would you be changing your opinion? Yes or no? What about your friend? And so what's your friend's hypothesis going to be? Your friend is going to say, this is that is the common point where you and your friend meet, right? Based on this data, you say it only rains when it's orange and foggy. And the point here is you're learning from experience, right? And we are trying to compose an AI, or we're trying to come up with a set of rules from experience. You and your friend could be two computer systems. And as with each observation, each of you, the optimist and the pessimist, keeps developing their hypothesis, refining their hypothesis. In the first case, you started off saying it never rains, right? And he says it always rains. After your first experience, you're still retaining the most pessimistic view. He retains the most optimistic view. And so you say it only rains on orange, smelly, foggy days. Then after your second experience, you retain the most pessimistic view, which is to say it only rains on orange, foggy days. His optimistic view is that it still rains. It always rains. Then after the third experience, it wasn't orange or foggy, and it wasn't raining. So you can keep your pessimistic opinion. His optimism has to be tamed a bit. So he says it rains when it's foggy, or it rains when it's orange. Because those were the two conditions under which it was raining, right? So here's what the first three observations gave you. And then the fourth observation was that you had an orange, smelly day when there was no fog and there was no rain. So his hypothesis of it always rains when it's orange fails, because this was an orange day and it didn't rain. So he has to sort of agree with you on this one rule, right? And that's going to be a final rule. Then you can make more observations, and subsequent observations do not contradict your hypothesis. So now we have a report to send. You send a report back to Earth saying, whenever it's orange and foggy on the planet, it rains. And so those are the days on which you can go to the planet and gather water for Earth and save Californian surfers. So this little algorithm that we saw, it's one of the oldest algorithms for machine learning. It's what's called the version space algorithm. And what it does is it finds a rule that answers yes to the question. This was a very kind of facetious example, but the specific kind of rule it found was it finds the combination of features that definitively indicates the class. And this is, and so, but you were asked to find a rule, except this rule was found by learning from experience. Each of you started off with the most pessimistic and most optimistic hypotheses. And as you observed more and more data, you modified your hypotheses till both of you met in the middle. And the place where you met was the final set of rules that you chose. So there's a bias over here. You're sort of starting with this optimistic and pessimistic views, and you think that this is a natural thing to be doing, but this is a problem. It turns out this is not a really good solution. Why so? This assumes that you and your optimist friend can meet at some point, that there's a single combination of features that can predict the answer. So this is what they call the induction bias in the entire model. There's this built-in restriction on what kinds of things the model will consider. And so if we go back to our human biases, for example, we have an induction bias that favors detection of upright faces in our brain. And that's part of the reason you see ghosts. That you don't want to miss faces, but you're going to see faces. So it comes at the cost of seeing faces where there are none. But anyway, going past that, if the data doesn't fit the bias, like when you had the upside down faces, this will not work. So for example, let's say you make one more trip and you end up on a clear, smelly, foggy, clear day, no smell, no fog, and it's raining. So your colleague's original hypothesis was valid, but there's no way for him and you to meet at one single point. So this kind of model construction framework cannot accommodate observations that allow for multiple conditions under which the outcome can be yes. So when you have a situation of this kind, you like to use a more complex framework for extracting information. And now, all of you are familiar with this, you'd use something like a decision tree. You're going to answer yes or no to each of your features. And you have a little tree of combinations, and that tells you when to expect rain and when not to expect rain. Now observe again that whether I'm using this version space model or whether I'm using this decision tree model, what I am really doing is composing rules. So all of this goes back to the fact that when you had classical ML, classical machine learning followed classical AI, classical machine learning focused on extracting rules that could be fed into classical AI for inference. And so a decision tree is just a somewhat smarter way of extracting rules where you can have disjunctions. And of course, they're very powerful. They can be learned from data. You know this from your machine learning classes. They permit multiple combinations of features to detect a class, but they run risks. They are not unique. So here's another decision tree. This one too is going to get the correct answer for this table. And in our case, this decision tree is actually the same. The two are effectively the same tree. But anyway, so I have these two different decision trees, both of which give me the correct predictions for the observations that I got from my visits to the planet. Which one would I use? This is where we learned. Always choose the simpler model, because in the most general case, the simpler model is always the correct choice. This is based on this famous quote by William of Ockham, Occam's razor, which is in Latin, so I won't try to read it, but basically says don't multiply entities unnecessarily, or in other words, given multiple models which give you the same answer, choose the simplest model that invokes the fewest variables. And so here, the lower tree with the smallest number of questions being asked invokes the fewest variables. That's the one that you would choose. And now again, going back here, there's two kind of mechanisms we saw. The version space or decision trees, they form rules for classification. So now there are basically it says reports back to Earth the kinds of conditions under which it reigns. So this is more like categorization. These algorithms that we just saw, you can think of these as saying identifying the specific conditions under which a class happens. So if you know, going back to our problem, if you want to know to send a spacecraft to this planet to collect water, then these are going to say go there when it's foggy or go there when it's clear. It's categorizing the combinations of features that give you an answer of your choice or that you want. Or for example, reporting conditions under which cancer may happen. When you know, there's elevated eosinophil count or muscle pains or lymph nodes, cancer can happen. It's sort of this is about categorization, but the problem that we are more familiar with is using this categorization for classification. You reverse the problem and say it's orange, stinky, and not foggy. Is it going to rain today? And the same rules can now be used to answer the question. These are two very different processes, except the same model can be used for both. This person has elevated eosinophil count, muscle pains, and swollen lymph nodes. Can this person have leukemia? You can answer this question. But then this leads to, you know, the obvious next step. Classical AI tabulated or graphed knowledge and knowledge rules and instructions. And classical machine learning extracted this knowledge or rules from data. The more data you see, the more you will learn. But then you can run into situations where this process of extracting rules can get you entangled in contradictions or make you just too specific. So for example, here, if you say it only rains when it's orange and foggy, it's going to be contradicting other choices, number one. And if you're going to be using that set of rules to you know, decide when to go to the planet to collect water, it's too specific and you're losing most of your opportunities, right? So this is where we step on into from classical machine learning, where you try to extract the kind of knowledge and rules that classical AI used into statistical machine learning. You hedge your bets. Do what is statistically most reasonable. Let's go back to our surfer problem. Let's say you aren't sure you got it right. You're really a pessimist, terrible pessimist. So you revisit the planet a few more times for more readings. And to your horror, you find that you get conflicting readings. So you find that sometimes on days that are orange, smelly, orange, not smelly and foggy, it rains. At other times, it doesn't rain. So you have recordings of identical features with different outcomes. So otherwise identical days on which it rains sometimes, but doesn't rain at other times. So now your clean narrative of either the tree or the rules broke down, right? Neither of these models is going to fit because these data defy that rule-based narrative. They just don't work. So you end up with contradictions. And so now you have to change your perspective. The question we asked, if I were thinking of it from a classification perspective, if I were to switch to a medical question, which is a little less facetious than our silly planet problem, you can say this person has elevated eosinophil count, muscle pains, and swollen lymph nodes. Could this person have leukemia? And if the data you observe are contradictory of this kind, like so, then your rules are not going to be able to allow you to answer it. So now you have to change your perspective. The perspective you will say is, of all the people who reported elevated eosinophil counts, muscle pains, and swollen lymph nodes, what fraction had leukemia? So this is a completely different question. This is trying to ask for a binary answer, and you find that you cannot really give a binary answer based on your experience. So you change your perspective and say, of all the people who had these symptoms, how many had leukemia? So if I were to begin drawing pictures, so let's say this is eosinophil count, and say this is swollen lymph nodes, then we're going to say, here is a reading that I got. Instead of asking, does this person have leukemia or not, I'm going to say, what proportion of people who had exactly this reading had leukemia? What proportion of instances at this location have leukemia? And now the problem becomes that of finding this proportion. And that's what we're going to learn from experience. Being able to compute this proportion is what we're going to learn from experience. And again, you're going to collect your training data. This is your experience you're going to learn from. And each training data instance is going to be a point in the space. The red dots represent people who had leukemia. The green dots represent people who didn't have leukemia. And you're going to guess the proportions from this training data. And the question is, from all this training data, can I answer this question? What proportion of training instances at this location were red? And the problem is, unfortunately, there are no training instances exactly at this location. And so we have to guess what proportion of people who had exactly these symptoms would have had leukemia without ever having seen in your entire data even one person who had exactly these symptoms. And so you have to somehow guess this from your neighbors. The simple thing you can do, you can draw a ball around this point and say what proportion of instances within this ball are red. You can keep, but what if there are no neighbors within the ball? Or what if there are too few neighbors? And what do I mean by too few? What is the radius of the ball? You end up with these questions. The standard answer that you have encountered in your machine learning classes is you're going to expand the ball until it includes some k neighbors. This is your k nearest neighbor classifier. And then you would compute the fractions of the two classes within the ball. And that is going to be an answer. But then can you really depend on it? Can you really trust this? Especially if this black dot is very far away from all of its neighbors. And you really had to expand the ball to count. So are neighbors that are far away as informative as neighbors in the vicinity? You can be sure. So instead of restricting the size of the ball, we can say, okay, let me consider everything that I ever saw in my training data. And so to decide, to estimate what fraction of people who had these symptoms would have leukemia, I'm going to consider all of my training data except the contribution of any training instance to the prediction I make over here. I would like it to fall off rapidly as the distance of that instance from my current point increases. So even so, you still have a problem, right? Why? Your training instances are also just samples. So if I got all of these training instances and I began using these training instances to make predictions out here, I'm sort of implicitly assuming that the training instance is some kind of a gold label. It's a gold standard. And this training instance is a sample. It could well be that people with exactly the same symptoms as the one for this training instance can both have leukemia and not have leukemia. And I just happened to draw one sample from it. So the fact that I got a red sample at this location doesn't necessarily mean that everybody at this location is going to be red. It just means that my best guess is there are more reds than greens at this location. So you can see the uncertainty begins to spread. Going back, firstly, we are sure, we believe that people with a specific set of symptoms can both have leukemia and not. Guess the proportion of people at this location who would have had leukemia. But since we never saw any instances over there at that precise location, we are beginning to look at the neighbors. But when you look at the neighbors and begin to make your inference from the neighbors, you're sort of implicitly assuming that the neighbors represent some kind of ground truth. Your training labels represent some kind of gold label. Whereas the fact of the matter is that even your training samples are just samples. Each of these guys in turn was drawn from that point, and you are sort of hoping that it's typical of what happens over there, but it certainly doesn't mean that everybody who comes from this location is green. So now you have to begin factoring in the fact that even the data that you use to figure out how to make your predictions are themselves uncertain. This is not because your data are noisy. This is because this is how the world is. It doesn't matter which problem it is. It doesn't matter how you collect your data. Your data are noisy more often than not because the world is a probabilistic place. People with exactly the same symptoms as this guy over here will sometimes have leukemia and sometimes not. The fact that this guy did have leukemia in my example just indicates that in that specific location, I have reason to believe leukemia is more frequent than a healthy person, but that's it. So we have to sort of figure out the proportions over here from uncertain data, where uncertainty is part of the problem. And so what we really need is to be able to compute what is the probability of the class, leukemia in my example, given the features, the specific location of the instance from my training data. So why don't we, considering that we're actually looking for proportions, and proportions are probabilities, instead of trying to just count stuff and begin making inferences, why don't I just model this explicitly? And when I model this explicitly, that gives you your classical Bayesian classification. You want to compute the probability of a class given features. And if you're familiar with how this goes, you use Bayes' rule to get, decompose it as the probability of class times probability of features given class normalized. So this first term is something that you will often assume changes from data set to data set. And then you begin focusing on the probability of features given the class for every point in the space. And you want to learn this from your data. And you want to learn this for the probability of features given leukemia, given a healthy person, the probability of features given people with leukemia, and from these you want to be able to compute your posteriors. The key ends up being the ability to compute the probability of features given class. We've seen in your machine learning classes, we've seen different ways of computing this. Your standard naive Bayes model says that the probability of getting a specific set of features for leukemia is the product over all features, is the probability of getting the individual features for the class. It's a simplifying assumption. You make more complex models that say, how can I get this what is the probability of getting this combination of features for each class. These are modeled by things such as Gaussian mixtures, hidden Markov models, Markov random fields, etc. Or instead of doing all of your standard Bayesian analysis, you can flip the problem and say, I'm not going to try to compute the probability of a feature given a class. I'm directly going to compute the probability of the class given the feature, which is basically what you really want. Instead of trying to go back and do what we do in Bayesian classification when we speak of statistics, which is to compute the probability of features for each class, we flip it around and say, let's address the actual problem we want. What is the probability of the class given the features? Or more explicitly, can I directly estimate the proportion of instances that will have exactly this combination of features that have leukemia? And now this function ends up being modeled by a model. And this is typically modeled by things like logistic regression, conditional random fields, or neural networks. And so this is the only mention I'm going to make of neural networks in this lecture. What your neural networks are doing is one step in this large scope of AI. AI is about acting intelligently, systems that act intelligently. They can learn to act intelligently by using machine learning. Machine learning can try to derive the kind of rules that classical AI used, or machine learning systems can naturally take into account for the fact that the world is an uncertain place. And so try to say, I'm not going to give you deterministic rules, I'm going to give you proportions. What is the proportion of all instances that had this specific combination of whatever that belong to whatever class? That is statistical machine learning. And deep learning, your neural networks, are specifically one mechanism to compute these posterior probabilities. So what you're going to be doing during the rest of your masterclass is not learning about AI, not learning about ML, not learning about statistical ML. You'll be focusing on this one little black dot right in the middle in this vast field of AI. And I have a couple more slides. I'll skip those, but I'll stop right here and say, there's a lot for you to learn. And I'm hoping that the next few days are going to be extremely instructive to you guys. And I'll stop right here and hand over to you guys instead of.
Thank you so much, Bhiksha. One thing that I'm always amazed about is how you finish on time. You seem to have the knack of pacing yourself perfectly to complete your lecture on time. So thank you. A fantastic introduction to the space to allow the students to launch into deep learning and learning about neural networks. So a big thank you as always to you for taking out the time and coming and talking to the students.
So if students have questions, I have a few minutes, or if you guys are.
Sure. There are a couple of questions here. So I guess Keshav asked, so basically through ML, we are trying to fit in between the best case scenario and worst case scenario. I guess that goes back to the version space conversation that you
So in the version space was I just gave you a couple of early models. I mean, decision trees are still very popular, right? But the whole point of the version space model was to explain to you how machine learning fit into the classical machine learning, artificial intelligence world. Classical AI was built on rules. So when machine learning first came into existence, it was all about trying to derive these rules so that you could just shove it into a classical artificial intelligence system. And of course, the version space model was a beautiful model which said, let me start off from two perspectives, the most pessimistic and the most optimistic. See where they meet. And that's going to give me the rules that I need for my AI. And the moment you begin doing that, you immediately realize that this is really not enough, right? This is so restrictive. It's going to give me one rule which probably works, but I'm missing most of the world. So which is what leads to this decision tree framework, which says, let me find all the combinations. And this is still, about composing the rule-based structure that fits into your classical AI. But the natural progression over there is that rules don't explain everything, right? There's no way you can get us but any kind of rules, any set of rules, which is going to give you the correct answer for both of these last two observations that you got. And so at that point is where you have to switch your perspective and say, okay, clearly this is not how the world works. This is not how I'm going to build an AI. Let me go back and take a step backwards and say, talk in terms of proportions. Because now when I begin speaking in terms of proportions, I can manage my risk. If 999 out of 1,000 people who have these symptoms have leukemia, I have to prescribe one thing. If 999 are healthy, I have to prescribe another. But you're not insisting that everybody is the same. You begin actually looking at proportions. That was your Bayesian formalism. That's what your neural networks are doing. Your neural networks are fundamentally Bayesian. They are computing proportions. And given the proportions, they are picking the most likely answer. And this is where you run into this problem, that the specific set of features that you saw in your data instance are never going to be seen in your training data. So how do you make the prediction? And if you try to make your prediction based on your training instances, it sort of ignores the fact that your training instances are themselves samples from a distribution. They are not gold standard. They never are. And that's where neural networks become really, 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 really powerful. And this is what you're going to find when you train your neural networks in the coming days. You will keep hearing of this term overfit. And you'll wonder what on earth is overfit. You're going to bandy this term around like crazy. And you're going to say overfit in response to all kinds of questions. And nobody will really know what overfit means, but you'll use it anyway. Here's what it means. You see these red and green dots? Overfit is when your neural network begins assuming that the entire world is red at this point, because it's not. It forgets the fact that this red point is one sample from a distribution, and that the distribution itself is unknown to you. And so the network will actually be trying to estimate distributions not just at these points you never saw, but at the locations of the training instances themselves. That is pretty amazing. And that's something neural networks are really good at doing. Anyway, I think I didn't answer your question. I went off tangent, but yeah.
Right, but I guess in a way, what the version space, I mean, if it didn't converge to one hypothesis, is defining a set of potential hypotheses, right?
Yeah.
Whereas a decision tree induction algorithm picks a decision tree and says this is the only one, even though there are other trees. So it's kind of an interesting algorithm from that perspective too, right? That it's actually giving you all the options rather than picking that one. Another question here, and this is of course from our friend Vikas Agarwal, who says there are other factors that determine precipitation, temperature, air pressure, and so on. Bringing out the point that an important factor here is also what features you're actually observing, right, for machine learning. Right?
Absolutely right. This is I couldn't make my table too big, but you're right. So right. Missing, so that's a beautiful point, right? This confounding table over here might have just been the outcome of my not having tabulated a fourth column, which disambiguates. That's something you're always going to have to be aware of.
Great. So, Diksha, that's the end of the questions here, and everybody's expressing their gratitude to you for a wonderful session. And really setting up this 5-day program the way you have. I'm really grateful for. So thank you.
So thank you, everybody. And it's always fun to talk to you guys. So if you have any questions,